So welcome back, everybody, and to the second sessions in Physics 4480. We are going to repeat some of the information which we had yesterday, and I also wanted to point to you where you will find the videos of the lectures. So this is the official website of the university, and then if you scroll down to the this fall semester, and I'm going to place the videos of the lectures. If you click on schedule, after every lecture, you will find a link here to the video of the lecture. And you can always revisit what was done. Yesterday, my handwritten notes, I had some problems with my tablet, but today the handwritten notes will be posted online, and you will find the notes there as well. You will also find the same link if you go to the website or the GitHub address of the course. So if you scroll down, there is at the README file. If you scroll down here, you will find a teaching schedule, a tentative teaching schedule, and you will see now that there is a link to a video. Now, what I do typically is that I upload these videos to YouTube, and YouTube gives also subtitles. So in case you have problems with my English, you can also see the subtitles. And the subtitles on YouTube, so Google has spent a lot of resources on improving this, this kind of option. So you can translate the English subtitles to Spanish if you want to. And I think they have in total 12 languages you can translate them directly into. So hopefully that can also help a little bit when you watch the videos. Now, obviously the videos are not of Hollywood quality. So this is just a raw recording of what was said here. So you will also hear my lame jokes now and then. Okay, this is the website. And as we discussed yesterday, there's a link to the Jupyter book, which functions as a kind of a textbook. It's something between weekly slides and something slightly more than that. But then we also have links to textbooks, which I normally recommend. And you will see that there will be typically reading suggestions every week. So if you go to the weekly material, which we discussed yesterday, you will find, if you scroll down a little bit here, you will find the recommended textbooks. And then there will be something like a weekly plan. And here also you will find the video of yesterday's lecture. And you will similarly find today, a little bit later, the video of this lecture. Yeah.
Can I ask a question about the books?
Yeah.
Are they equivalent? Like, is there? Can I just pick one and read in it, or should I sort of try to read all three of them?
So what I would typically do is to come with reading suggestions which are relevant to what we cover from one of these textbooks.
Okay.
These textbooks which we have here are kind of standard textbooks. So Szabo Noslund, the first 3 chapters are very much linked to the beginning of this semester. But then when we move on a little bit, Shavit and Bartlett will be a little bit better. They often, in this textbook by Shavit and Bartlett, which is a kind of standard for this type of many-body physics, they are a little bit sloppy with some of the linear algebra and so on, which is actually covered nicely by Szabo Noslund. So they've been teaching to quantum chemists, and they have often a slightly weaker mathematical background than physics students. So they spend a lot of time on linear algebra elements, which are essential for quantum mechanics. Quantum mechanics, as you will see it here, is to a very large extent linear algebra applied to physics problems. And then there is a textbook which focuses more on Green's function theory, which is also a very popular one. So if you're more inclined towards field theory, if you're taking quantum field theory, for instance, or if you've taken it, then Nagel and Noland is actually one of my favorite textbooks. So this is a little bit more advanced, whereas Szabo Noslund and Shavit and Bartlett are more at the kind of level which corresponds to this course. So I will pick a little bit from here and there. And if you go to this link, by some kind of a strange magic, you will find PDF files, PDF versions of these textbooks. Some of them are out of print, so you cannot get them. I think Nagel and Orlando is a little bit difficult to get, but there are PDF files, and also of Sabo and Oslo, there's also a PDF file of the solutions. Okay, so this was about practicalities. I just wanted to quickly repeat some of the things we went through yesterday, and then go immediately back to the tablet, and then we will stay with that one. So as we mentioned, one of the important things of what we will do is to define a computational basis. That computational basis is normally going to be an orthogonal basis, and often normalized as well. We normally call that ONB, orthogonal and normalized basis, which is the solution to parts of the problem. So this could be an atomic system where you can solve the single particle problem and obtain the exact solution, but then you don't have the exact wave function because you have also an interaction. And when you add the interaction, you will often expand the true solution in that basis. So we are going to remind you a little bit about these things. And in the beginning here, we just discussed some basic notations. So a typical notation we are going to use throughout is a Dirac bracket notation, which means essentially that a vector, this column here, so vectors are just columns in this notation here, is just given by the this Dirac notation. And then we have the emission adjoint, which is given here. So sometimes I may be a little bit sloppy when I talk about the emission adjoint. I will just call it the adjoint, or sometimes I will call it the conjugate adjoint or whatever. So sometimes my wording is going to be a little bit sloppy when it comes to that, but you know what we mean. So mathematically, this is what we mean by that. And you will see that in textbooks as well, that sometimes the textbook can be a little bit sloppy with language. The thing I just wanted quickly to bring back again, besides these quantities here, so outer products play a very important role. We are going to meet projection operators again and again and again. And these are things which play a very important role, especially when we deal with many-body perturbation theory and projections of the full problem into a smaller effective Hilbert space. So whatever we are going to do, we will always have to make truncations. So our Hilbert space is in general infinite, which means that we have to make some kind of projection to a smaller space in order to be able to run calculations. So projection operators are some of the kind of kitchen items which you will see again and again in this course. And we discussed some of them here. You can see in the definition of the computational basis. And I just wanted to repeat some of these on the whiteboard, so we can, write them down and keep them for later use, because these are things which we are going to use again and again. And secondly, there are also topics which deal with the definition of the computational basis. So in the examples which you will see here, we have just defined two basis states, 0 and 1, which are defined like this. And these computational basis states, they could represent a two-level system. And you could think of that as your system. And you see also that these states are orthogonal, and they're also normalized. And then you can define these projection operators. And what you will typically see then is that this operator P, if you have a linear combination like the one you see here, if I act with this operator P on this state psi, that projects out the component 0 with an amplitude alpha. And similarly, if I take the operator Q, that projects out the other one. And it's going to be pretty common when you do many-body physics that you are going to define an effective Hilbert space, which is defined by, let's say, a projection operator like this one. So you can define an effective Hamiltonian, which you then can use to study, let's say, the eigenvalues and eigenstates of a specific system. That means that if you can do the true calculation, you would have a recipe to find an effective Hamiltonian which lives in a smaller space. And much of many-body physics deals actually with this. So sometimes you can do this in a rigorous mathematical way. In other cases, you simply say that I am going to truncate my space. I cannot quantify how I do it. I just do it because I believe these are the degrees of freedom which are of interest. Okay, so what I wanted to do is more to switch over to the whiteboard, and we are going to repeat some of these elements, and then we are going to move over to the definition of the Hamiltonian, and we are going to look at how we can build a trial wave function which can be used to calculate expectation values. And we will start with a two-particle problem. And then we are going to generalize this to a many-particle problem. So this is going to serve as a kind of starting point for the different many-body methods. And many of the expressions which you will see are also going to serve as a kind of calculational ingredient or tool, which we will use in more complicated many-body calculations. So let's look at some of these basic elements here, which we are going to need. So let me switch to the whiteboard. Get rid of this one. Okay, so the one of the things which we started to discuss yesterday was this topic about a computational basis. So let me quickly remind you of that, because that plays a very important role. And a very simple example was this two-level system, which we discussed yesterday. That is a two-level system. Where we could define one state, which we called phi 0. And this could be now be given by this state here, this spin-off. And then we had a state phi 1, which we define in terms of this 0, 1. And the whole idea here is that we want to have an orthonormal basis. So we normally call this an ONB basis. And we see now that if we take the overlap of phi 1 with phi 0, this is equal to 0. So it's pretty straightforward to run this calculation. Now, the other thing which we defined was a so-called projection operator, which means that we could define an operator which is now given by the outer product. So remember now that if I do this, phi 0 and phi 0 here, this is an outer product, because what it means is that what we have now is this specific operation, and that gives us a matrix. So it's not the inner product, but it's the outer product. And that gives us an operator P, which looks like this, as it's a 2x2 matrix, 1, 0, 0. And we have also the possibility to define a new operator, which will be this phi 1, phi 1. And we see immediately that that gives us a new matrix, 0, 0, 0, and 1. So when we sum the two, we get the identity matrix. So which then defines the completeness relation for these two states. So let's just change page. Everybody gotten this? So let's just wait a little bit. So I'm putting hats on quantities which are going to be operators. So these are, in general, operators are going to be matrices in practically all kinds of applications which we're going to study. So P is an operator which now is going to operate on a state. So it's going to be a matrix multiplied by a vector in linear algebra language. So let's continue here. So if we now take this P and multiply that with Q, if you multiply these two matrices, you will see immediately that this is equal to 0. And that represents the fact that we have constructed a matrix from states which are orthogonal to each other. The other thing which we have is that P plus Q is given by the identity matrix. And what we see then is that this is 1, 0, 1 here. So that's the completeness relation for that specific system. In general, what we will have is the following. We will have a state P, which now runs over a given orthonormal basis. It can be any basis. It could be a basis which is an eigenbasis of a specific operator. It doesn't need to be the energy operator. But we would then have a basis where we start with 0, and then we go up to a dimension d minus 1. So d is a dimensionality of this specific space, which we have defined. And yesterday we defined the effective Hilbert space in terms of this d. And then we have an orthonormal basis, like this. So this is an OMB. And then we would have another operator, which is often referred to as the excluded space, or the exclusion operator. And this will be a sum which starts with D and goes in principle to infinity. Now, one important feature of these operators is that they are what we call idempotent, which means that if I take P squared, that gives us P. And you can see that immediately if you take the example in the previous case. So if you do the example with 1, 0, 0, and you square it, so that means you have 1, 0, 0, then you see that you just get back to 1, 0, 0, 0. So these are operators which are equal to themselves when we square them. And then we have Q squared, which is also equal to Q. And since these operators are defined by states which are orthogonal, then we will also have that they commute with each other. So these are important properties here, which we are going to use again and again and again. So to illustrate this in connection with a given basis. So yesterday we looked at the hydrogen-like basis. Another very popular basis is the harmonic oscillator. And that's the solution to the harmonic oscillator problem, where you have kinetic energy plus a harmonic oscillator potential. So if we take a closer look at that one, we could now think of a computational single particle basis. And I'm going to use an acronym SP for single particle. So that's a single particle basis. So we could now take as an example the harmonic oscillator, and we could take the harmonic oscillator in 2 dimensions, just to give you an example. Harmonic oscillator in two dimensions. This is a very popular system if you're thinking of semiconductor physics, nanotechnologies. I mean, quantum dots, for instance, these are electrons which are squeezed down and move in roughly 2 dimensions. These are systems which can be produced in the lab. You can trap a single electron in small areas, and you can actually manipulate them. So quantum dot systems are actually used as a candidate systems for making quantum gates, for instance, and construct quantum circuits and perform quantum computations with microscopic devices. So harmonic oscillator in 2 dimensions, if we now make a drawing of the spectrum, we know that we have quantum numbers nx and ny. These are the quantum numbers when we deal with Cartesian coordinates. If we don't have Cartesian coordinates, we can make a transformation to polar coordinates, but we will still have 2 quantum numbers because we are in 2 dimensions. So nx and ny represents the nodes of the wave function. The wave function is now given by, so what we will call now psi. And now we are going to set up this definition, which we used yesterday. So we have a state, a one body state. So there will be an nx for a single particle state. So there will be that state. So that's the single particle degree of freedom in the x direction. And this is going to be given by a Hermite polynomial defined by nx. And it has the coordinates x. And it goes like e to the minus some constant multiplied with x squared. And I'm going to write this constant just as a constant alpha. That's a one-dimensional problem. Now, the ny is the same. So we would have ny here, and then we have y, and e to the minus y squared of some parameter alpha. And then these numbers nx and y, they take values from 0, 1, 2, etc. Now, in principle now, the two-dimensional wave function is given, as we discussed yesterday, by the tensor product, by the tensor product of nx and ny. So you could now think of nx, the part, you could have a set of values x. So suppose you have 10 values for x, that would be a vector with 10 elements. And if you have 10 values of y, that would be a vector with 10 elements. Now, we are going to hide that information because we want to have a more compact information. So the way we will typically write this is in terms of this nx and y, like that. Okay, but just keep in mind that also when we add spin to this, there is an additional part with spin. And for this case, which is a single particle case, so when you add spin, if we do that now, and we are going to assume that we have a spin half object. And that means that there's going to be a projection of ms equal to plus minus 1/2. We will essentially stay with this type of fermions in this course. Many of the methods which we're dealing with can also be used for bosons. You can increase the spin value of a given particle. You can have spin-free half. So if you're doing nuclear physics, you may have particles like isobars, which are excitations of a nucleon, which have spin-free half, and so on. But we are just going to keep this spin equal to a half throughout the course here. And that means that what we will have then will be a wave function of nx multiplied with a wave function of ny. And then we have the tensor product with the spin part, which I just write like S and ms. But we will just write this when we are writing the full wave function. We are going to write it in this more compact way. So that means that we will have it like nx and y, and then we will have s and ms. And this would often just be collected in terms of one number. So that means that there would be a state which is now labeled with a number, let's say A, like this. So A now contains these specific quantum numbers which label these different states here. And you could let A now run from, if we start with 0, so I often start with 0 because when I write codes in Python and C++, arrays start with 0. But that's just a numbering, so it's up to you to choose. So if you do that, we could have such states like that up to infinity in principle. But we will truncate this at a given value d. So that means that we would stop somewhere at d minus 1. So if you now think of the harmonic oscillator and we translate this into a spectrum, what we would have then would be a spectrum like this. So these numbers takes values for nx equal ny equal 0. And now you could think of one state with spin up and one state with spin down. And then you have the next one where you have a degeneracy. So in this particular case with the harmonic oscillator, you have nx equal to 1 and ny equal to 0. and you have an ny equal to 1 and nx equal to 0. And now you have, again, since you have added spin, you have a spin up and spin down. So when I say spin up, if I look at the projections of the plus 1/2, I'm going to label that one with a spin up. And if I have a projection minus 1/2, this is just going to be a spin down. But this is just a labeling, which we have chosen. And then you would similarly have a spin up here and a spin down. And the energy difference here is so that if we look at the energy of the system, the energy of the harmonic oscillator does not depend on spin. So the Hamiltonian for the harmonic oscillator is spin independent. That has important consequences when we calculate the expectation values, which we will come back to. So the energy for the harmonic oscillator is given by the h bar omega, the oscillator frequency. And then you have nx plus ny plus 1. 1 because you're in 2 dimensions. If you're in 1 dimension, you have a half. If you're in 3 dimensions, you have 3/2, etc., etc. And then that means that when the energy difference here, let me do that. The energy difference between these states is 1 h bar omega. So these are excited states. And you can now start filling in particles. So if you have only 2 particles, you can actually let them be excited to the higher lying states. In principle, now you can continue this machinery which we have here. So we can have new states. And in this case, we would have nx equal 2 and ny equal 0. You can have nx equal ny equal 1. That will give an energy of 2 h bar omega. And you will have actually 3 h bar omega because the ground state has h bar omega. And then you have an nx equals 0 and an ny equal to 2 here. And you can put in the spin numbers. So if you have only 3 h bar omega, 2 h bar omega excitations, you can have 12 states in total. And you can continue this way. And in principle, when you look at the harmonic oscillator, you have an infinity of solutions to the harmonic oscillator eigenvalue problem. So when you want to construct a computational basis, you have to put a limit. So in principle, this goes up to infinity, but we will put somewhere, we are going to put a limit here. And this is going to be a limit which now defines the last state we include in the calculations. So everything which we have here is given now by an orthonormal basis. So we could say now that the problem we are dealing with mimics that of a harmonic oscillator. And since it mimics that of a harmonic oscillator, we are now going to expand a solution to the problem in terms of harmonic oscillator states. So if you now look at the notation which we have here, this specific notation which you see up here, this one, this is now going to be one of these states. And in every case here, we can now put in slots. So we could say this is slot 1, this is slot 2, and this just continues. So you could put labelings here where this is 0, 1, this is 2, 3, 4, 5. And every time a particle is in there, this slot, this number 4, for instance, points to the specific quantum numbers. So this one would then point to the specific quantum numbers, which label that one. So in a computational way of thinking, what it means is that you have allocated a vector, which now has these different numbers, 0, 1, 2, 3. And each one of them points to another set of arrays, which contains nx, ny, s, and ms. So that is what you need to specify this specific system. There's a reason why I'm doing this. It sounds trivial. The reason why I'm doing this is that in just a little bit more than a week, we are going to start with second quantization. And in second quantization, we are not going to be interested anymore in these quantum numbers here. They will just be numbers where the creation and annihilation operator point to specific quantum sets. So when we deal with second quantization, we are going to take away, like, let's say, the spatial degrees of freedom. And every such slot here is going to be represented by an operator which creates or destroys a particle in that specific slot. And that is a very compact way of thinking and representing wave functions. So everything I'm doing now is actually preparing us for a compact representation of many-body system. So this is it sounds like a kind of boring technicality, but it's going to be extremely useful when we then want to represent a complicated many-particle wave function. Okay, when we have this kind of representation here, what we are going to do next is actually to represent a given state in terms of this basis. So we can always expand in terms of the harmonic oscillator basis. So we can expand. A new state in terms of that basis. And that new state could be a psi, which I just defined like this. And this is going to be given by a sum over all the states which I have. In principle, this runs over the infinity of states. But we are going to truncate that sum because we cannot deal with infinities. So that means that there's going to be an overlap coefficient. And then, since I use these Roman letters to represent the harmonic oscillator basis, then I have a set of states here, I. So if you go back to what I did in this slide here, you see now that I let these Roman letters represent all these quantum numbers. And just keep in mind then that these quantum numbers, the way it's represented, is actually when you want the wave function, when you want the actual wave function, it is the tensor product of all these wave functions here. Okay? So because we at a certain point, we skip all the tensor products just for simplicity. But underlying, if you deal with spin and spatial degrees of freedom, there is a tensor product between the spin part and the spatial part. Okay, so let's keep moving here. So what we can do now is to construct a state like that. Now, the next thing which we could do is actually to define spectral operators, but I'm going to leave that a little bit because I wanted to get started with a many-body state. And the simplest system we're going to look at is two particles. What you could think of now is us wanting to describe a system of two electrons which move in a harmonic oscillator potential. So what it means is that we would have some kind of trapping potentials. So we have two particles or two fermions in a harmonic oscillator potential. Harmonic oscillator potential in two dimensions. So in one dimensions, and this is actually me who has problems in moving beyond one dimension. And as you probably heard, my wife always thinks that I'm a very one-dimensional person. And my daughter agrees with that as well. It's always been like that. But anyway, so that's why you will see this in one dimension. But you would have two particles and they may interact or they may not interact. And we need an ansatz for the wave function and we need also an ansatz for the Hamiltonian. So let's try to use what we had here now for these, with these single particle states. These are our basic computational states. And what I want to do now is to build an ansatz or a guess for a two particle state based on that. So the first thing I'm going to do now is to define the Hamiltonian. So we're going to have a Hamiltonian here And I'm going to write my Hamiltonian in a specific way. So H, and it's an operator, it's going to be given by one part H0, and H0 is normally going to be linked with a computational basis. So a part of the problem which you can solve analytically, or you can solve it exactly numerically within numerical precision. So typically H0 is a part of the physics problems which you think you can solve. And then we have the interaction piece. So I here stands for the interaction between the particles. So this H0 is assumed to be a part of the Hamiltonian which we can solve analytically, or which we can solve easily. So the wave function does not need to have an analytical expression, but it could have a numerical representation, but it is exact to numerical precision. There are very few problems which we can solve analytically, but some of these problems are actually very useful, because sometimes when we calculate expectation values, there are some integrals which can actually even be solved analytically. And that makes life much simpler. Yes?
So is there an assumption that the interaction Hamiltonian is sort of much smaller?
We don't need to make that assumption.
Okay.
We don't need to do. But the thing which is important with that question which Morten raised is that the assumption we are making now, where we use a single particle basis to make an ansatz for the many-body wave function, that assumes that a single particle picture is a viable picture. It's something which is useful, which gives a good representation of the system. So if you go to atomic physics, the single particle degrees of freedom gives something like 70 to 80% of the contribution to the total energy. And then the interaction, the Coulomb repulsion between the electrons gives the rest. If you go to strongly interacting quantum gases, like a helium-3 or helium-4, you have a kind of a Bose-Einstein condensation, then in that case, this single particle picture, which we have been discussing now as a computational basis, doesn't make sense. So most of the wave function is actually determined by two-body correlations or more complicated correlations. So it depends what we are doing now. The way you build the computational basis tells you a lot about what is a meaningful starting point. And keep in mind that if you now look at the, let's say, a harmonic oscillator potential with anharmonicities, which is a very popular topic, in that specific case, the harmonic oscillator solution is not an eigensolution anymore. But you could expand the exact solution in terms of the harmonic oscillator one, and you would actually calculate this one, which would then be the exact solution. So this expression, which you see here, is actually very important. And these coefficients which you see, they are represented normally by unitary transformations. So if the basis is orthonormal, the new basis is also orthonormal. That's one of the properties which you may have seen about unitary transformations. You will find that, proof for that, in the lecture notes as well, if you have forgotten this piece of linear algebra. So that's a very important. So what you see here is actually, it looks very simple, but if we have a complete orthogonal basis, we can expand any beast in that basis. And you will see later why this can be handy when we solve many-body problems. Okay, so let's define these Hamiltonians then, which we have. So if we take H0, so this is the sum over all the individual single particle pieces of the Hamiltonian. So in general, if you don't have an external potential which confines the motion of the objects, you're just going to have kinetic energy. So we would typically write this as a sum from 1 up to n, the number of particles. So uppercase n is going to refer to the number of particles in the system. So this is number of particles. And we are going to rewrite this as an H. I'm going to put a hat, and then it's going to be defined in general by the positions of the particles. So many of these operators will just depend on the position, but you can have spin-dependent operators as well. So if you add a magnetic field, for instance, then there will be an operator which changes the spin of the particles. But let's assume it depends only on the spatial degrees of freedom. So this H0 of x of I is going to be given by the kinetic energy operator, which I now just write in terms of the second derivative, and I haven't specified the dimension of the problem, plus an external potential, which confines the motion of the particles. So if you're doing atomic physics, this will be the attraction from the atomic nucleus. So I'm just going to write this as a U external, and this has also a spatial dependence, but it doesn't need to have only spatial dependence. Later, we will generalize this to be an operator which depends on both spins and spatial coordinates and other necessary quantum numbers. So this is the operator, and the assumption we have made now is that when this operator H0 acts on this state I, this is a very important assumption, this is now an eigenstate of this H0. This is a very common assumption. So this is eigenstate I of this state I. So this is an assumption we often do when we deal with many-body physics methods. Okay? And the reason is something you will see a little bit later, but it allows us now to make a many-body basis based on a single particle basis. And that single particle basis is the solution of a part of the problem. The full Hamiltonian is then given also by the interaction piece. And let's set up that one before we take a small break. So the interaction piece is typically in this course, we will stop with two-body interactions. But if you're dealing with nuclear physics problems, you will have three-body, four-body interactions because you don't have a true expression for degrees of freedoms of protons and neutrons only in nuclear physics. You actually have an effective Hamiltonian, which comes from quantum chromodynamics, where you have quarks interacting with gluons and with themselves. And this interaction here, if you want to rewrite that in terms of a non-relativistic interaction, you get effective two-body, three-body, four-body, and infinitely body interactions due to the underlying degrees of freedom of quantum chromodynamics. If you want to have effective degrees of freedom in terms of protons and neutrons only. But we are just going to treat this as a two-body interaction. There's a limit to how much complications we can add into 10 credits, period. So this is a double sum, I and j, and it contains then a potential which depends on xi and xj. So this potential which you have is in general a translationally invariant potential. And it depends typically only on the relative distance between the particles. So that means that this is normally given by the relative distance between two objects. And let me just end this one. So since we are staying in two dimensions, this will be given by xi minus xj squared, and then we have plus yi minus yj. And if you have higher dimensions, you would have the additional coordinates. So if you have a Cartesian coordinates in 3 dimensions, you would also have the z coordinate. And then this just continues. So most potentials, which we know in nature, depend only on the relative distance. And that makes the potential or the interaction translationally invariant. That's a very important feature because that's a very important symmetry. which also simplifies a lot of many-body physics. So this is some of the basics. So after the break, we are going to calculate the expectation value of the energy of this specific Hamiltonian. And then using the property which you see here, that we have assumed now that this is a eigenbasis of this specific Hamiltonian. And the final property is that I and j is given by delta ij. That's an important property. So don't hesitate to ask questions. Things are unclear. And maybe we just take a small break right now, if that's okay with everybody. Just put the recording on pause. Okay, so let's get back again to the problem here. So we have defined the Hamiltonian. So there is one part of the Hamiltonian which just acts on one particle at a time. And that is the piece you see here, this one. And then you have a part of the Hamiltonian which acts on two particles. Clearly, you can have more complicated Hamiltonians. You can have effective free body forces, etc. But we are going to stay roughly with the Hamiltonian, which has these basic features. Many of the Hamiltonians will have interactions which are rotational invariant, and that gives addition to other symmetries, which means that angular momentum will be a conserved quantum number. So every symmetry which you have in your Hamiltonian leads to a conserved quantum number. And I guess you've seen some of these things before in basic quantum mechanics. So we will, by the way, not pay much attention to specific symmetries except the translational symmetry, which is actually important when we are calculating many expectation values. But clearly, if you don't have a spin dependence in your Hamiltonian, it means that the total spin of the system will also be a conserved quantum number. So let's move on a little bit and start looking at how we can now make an ansatz for a trial wave function. So what I said is that we had a single particle wave function, which is given by this states I, which is an orthonormal basis. So now we're going to make an ansatz for a two-body wave function. Or two-body state. So sometimes I'm a little bit sloppy with wave function and state function. So normally when we think of a quantum mechanical wave function, we think of the solution of the time-dependent Schrödinger equation. But then we often sloppily refer to a state function, which only depends on the spatial degrees of freedom, as something which also is given by the wave function. So I may be a little bit sloppy in my speaking, but normally when I write down things, I will call something which does not depend on time as just a state function. Okay, so we have this quantity here, and we are now going to have a function which will now depend on two single particle degrees of freedom. So that means that I'm going to make an ansatz of AB, and I write it like that. That is now the tensor product of two particle wave functions, like that. And since we are going to deal with fermions, we need to bake in an antisymmetry. So the antisymmetry is normally the simplest possible way we can set it up is by setting up a determinant. You've probably seen that before. So that means that the ansatz is going to be given by this 1 over square root of 2, and this will now be given by a determinant. And now what I will be doing here is to spell out these specific wave functions. So I will have a state here, a psi of A for particle 1, x1. But since these are indistinguishable particles, we don't know whether that is in slot A or in slot B. So that means that I have this one, and this is particle 1. So I will, in my kind of notation now, I'm going to let these different columns represent the particles and their positions, and then the rows will represent other quantum numbers. So this will be particle 2, and sorry, this is an A, and this is a B, and this is this X2 here, like that. And this phi of alpha X1 is what we encoded as this X1 B of A here. That is the specific encoding. And what we have is that H0 acts on phi of A of X1. This is the same as this epsilon alpha, now epsilon A, multiplied with phi A of X1. So this means, what you see here, means the same as the compact Dirac notation, which we had in the previous, on the previous slide. So while you're writing this one, after you've done that, we are going to go back to the previous slide. So if you look at this notation here, this one stands for the same as what we had here, except that there I use I instead of A. Yeah.
Is it implicit that there's a tensor product between?
So what is implicit now is that there is a tensor product at the single particle level. It could have a tensor product of the X and the Y degrees of freedom, spin degrees of freedom. So the only thing we've done now is that we baked in all possible quantum numbers here. And this is a wave function representation which now contains all the degrees of freedom. But when we did this, then we have just baked in the quantum numbers and we have left out the spatial degrees of freedom. So these are equivalent statements. So the reason why I did it is that when you end up calculating things in standard first quantization, this is a typical way you would set it up. And what I wanted to do now is actually to go through the calculations of the expectation value of the energy. Just as a small example, if we take this, suppose now that A is given by this state 1, 0. This could be a qubit state for qubit 0, or just a two-level system. And B is given also by 1, 0, like that. Then the state AB in this specific case is actually the tensor product, which then becomes, when I do the math here, 0, 0, 0. And then you can do similar tensor products with the other state from the two-level system. And then you would get 4 states, which also would be orthogonal. But we would typically represent everything in this very compact notation instead of writing this again and again and again. But just keep in mind that this is an underlying feature which you have to plug in when you run computations. Okay, so let's try now to calculate these announced eigenvalue expectation values. So what we're going to do now is simply to calculate the expectation value of AB with the Hamiltonian, not that one, but the full Hamiltonian of AB. So I will call this an expectation value because we're going from the same state to the same state. And when I have different states, we normally sloppily call these matrix elements because it's going to be represented in terms of a matrix, but they represent transition probabilities from one state to another state. Okay, so what we have now is that this function AB, which we have here, when we write it out, it's given by the square root of 2. It's normalized. So we have a phi A of x1, phi B of x2 minus phi A of x2 multiplied with phi B of x1, like this. This is a state. And now we're going to set up the expectation values of, so this is the first part we're going to do now, AB of H0. So next week, we are going to introduce a more compact notation, which will allow us to calculate the expectation values for many particles in an efficient way. Now we're just going to do this in a very, very brute force way. So what I'm going to do now is simply to write out the integral. So this is going to be an integral now, where I have a double integral over dx1 and dx2 here. And I'm simply writing out the wave functions and performing the multiplications. So this is not going to be very exciting, but I actually want to go through these steps. And then we are going to introduce another type of operators, which will allow us to calculate in a simpler way the same expectation values when we have many particles. But I wanted to baby step you through this more boring exercise first, so that you see the basics and why we can get simple expressions for a many particle system. So now it's only two particles interacting. So what we would have then, so we multiply with a half because we have a square root of 2 times a square root of 2. So we have the wave function on the bra side. So it's alpha B. So this should be an A, not an alpha. I don't know why I prefer alphas instead of beta of A's. A of x2, complex conjugate, and B the same. And here we have the exchange, which comes from the determinant, which we set up. And this is now multiplied with H0, acting only on x1, plus H0, acting only on x2. It's a sum of a single particle operators. You don't need to have an external confining potential. If you do, let's say, nuclear physics or particle physics, there is no external potential. What confines the motion is the interaction between protons and neutrons. But and in that case, you would only have kinetic energy. So this operator here could be kinetic energy. But now we are thinking that there is an external potential like the harmonic oscillator, which confines the motion of the particles. So harmonic oscillator, you can actually realize that in the lab. And this is done in systems which are called Penning traps or Paul traps, where you can set up electric quadrupole fields. And they go like x squared plus y squared. The Nobel Prize in Physics in 1989 was given to Penning and Paul for having devised this kind of traps. Yeah.
When you go from the left to the right, just by starting to identities between AB and H0 and H0 and AB, and so identities and then two integrals.
That integral, since it's two particles, I'm integrating the definition, the quantum mechanical definition, is the integral of all the degrees of freedom. So that's the, so I'm just taking the definition of an expectation value. So if you, let me just write down and then I'll come back to it. I'll try to explain it better. So I have this x1 times b x2, and that has a minus, and then you have phi of a x2, phi of b x1, and like that. So the question is more that, how did these integrals over dx1 and dx2 come from? So if you think back of a quantum mechanical expectation value, so let me just write, okay, I'm just going to wait till you have it. So if you think of a quantum mechanical expectation value of, let's say, the Hamiltonian which you have, you would normally write it like this in the kind of physics way. Or if you wish to write it in a more mathematical way, you could write it like this. And that is normally an integral over d tau, where tau is the volume element you have. And then you have the wave function as a function of all the degrees of freedom. And you have a Hamiltonian here, and then psi as a function of that one, and then there is a normalization integral. So this follows from one of the postulates in quantum mechanics. And this is what I've been using. So in our case, delta tau is equal to dx1, since we are in 2 dimensions, and dx2, the second particle, and dy2. So in general, to calculate this quantity is a multidimensional animal. So if you have 10 particles in 3 dimensions, this is a 30-dimensional integral. And that's why Monte Carlo methods are so popular, because then you would evaluate this in a stochastic way. So if I want to evaluate this integral in the standard way, what happens then, if I just do it in a brute force way, and you have something like 100 integration points, and you have 30 degrees of freedom, you find out that you will, even with the best computer now, you would need more than the lifetime of the universe to make that calculation. So, but in our case, since the interaction is a 2-body only at most, this problem reduces to at most an integral over 2 particles. So that means that if you have 2 particles in 3 dimensions, the integral is at most a 6-dimensional one. And that's something we can calculate. And if you take a basis like the harmonic oscillator or the hydrogen-like basis, and you have a Coulomb interaction, just to give you an example, you even have analytical answers for the integrals. And that's why some of these basis sets are so popular as computational basis sets. So this was one of the reasons why you often search for computational basis, which is 1, physically meaningful. So if I deal with atoms and molecules, I could think of using hydrogen-like orbits. If I'm dealing with quantum dot systems in semiconductor physics, I could think of using a harmonic oscillator as a computational basis. These will be physically motivated basis sets, and at the same time, they give us a computational benefit in the sense that many integrals can actually be calculated analytically or very fast numerically. And these are, when you deal with many, many particles, these become important things. We actually have people who've written their PhD thesis in many-body physics by just developing algorithms for calculating these integrals in the fastest possible way. Okay, so what we are going to do now is actually to take these expressions, and we need to use the orthogonality, which we plugged in here. So we have this orthogonality, and then we have this relation here. So we're going to use these relations now. So let's go back. And now what I want to do now is just take term by term. So I promised you this is going to be horribly boring. So we're going to take the first one, this term, multiplied with that one, and multiplied with that one. Okay? So let's just write it out. You will love me for this, actually. So let's do the first term. And then you will see the pattern here. Eh? You do this once. And then when you see the simplification you can do later, you will see why that simplification really makes a big change. So we have an alpha, now A, complex conjugate. This is the first term. B of x2. And then we have the 2 operators, h0, x1 plus h0, x2 here. And this is multiplied with I of x1 and b of x2 here. So if we now look at the first operator contribution, so this guy here acts only on this, and we know that that gives an eigenvalue of epsilon of A, because we have assumed that this is an eigenbasis of this. And you see you have x1 acting with x1 here. That means that the integral here has this term and this term, and since that's normalized, that gives us 1. So the first term which we have here acts only on x1. For x2, we have just a normalization factor. So that means that when we sum it up here, the first term gives us, so we have 1/2 here, and I have epsilon A, that's from the first term, and the second term gives us epsilon B, the two single particle energies. Because when I have the operator, this operator here picks this one, and that gives us this, but then I have the wave function here multiplied with the wave function here, and that is just a normalization integral multiplied with a constant, and that leaves out the constant. And the same with this term here, which then picks this one, which again picks that one, and that gives us this. That sound reasonable? So let's look at the second term. So the second term here is going to be a little bit different. So it's going to be 1/2, and then I have a dx1 and dx2 here. And then my second term is now a of x2. And then I have a b of x1. This is what we call the exchange term. And then I have the one body operator, x2. And this is multiplied now with a of x1 and b of x2. So if you just admire this expression here now, what should we get as an answer? 0. So let's see why we get 0. So the integral over x1 involves now this term here, and then we would have this one. So we take this, this, and this. Okay, this one acting on that gives us a constant times the wave function. But then, since it's an orthonormal basis, I have a b here, and I have a, and a is not the same as b. So that gives 0. And the same with the other term. So the third term gives the same, but then there's only the last term. So this is actually equal to 0. And same with third term, with the third one, where I then take the exchange term of the ket side and multiply with the first term. But the last term is given now by this. So the last one is a dx1, dx2 here. And then I have a phi of alpha of a of x2. So these are the two exchange terms multiplied with each other of x1. And then I have h0 x1 plus h0 x2 here. And this is again multiplied with a of x2 and phi of b of x1. So this term is not going to give us 0, simply because what we have is that now if I look at x2 here, that operates on this one, and that gives epsilon a, which again is linked with this one. So that gives a constant epsilon a. And the same happens with x1, which acts on x1 here, so and x1 here. So this is actually a number 1 here, not a number 2. Right? So this gives us simply 1/2 of epsilon a plus epsilon b. So that means that when I bring everything together, what I'm going to have now is that the expectation value of this specific part of the Hamiltonian is just going to give me the sum over the single particle states. So that means that if I do that, what I have now is that A of B, the two-body state, H0, of A and B is actually equal to epsilon A plus epsilon B. So this means the following. That means that when I take H0 with my ansatz, this is given by an eigenvalue, which is the sum of the single particle energies. So what we say now is that AB is an eigenbasis of H0. This is because I chose these specific single particle basis states as computational basis. So it means that I have a solution to the two-body problem for one part of the Hamiltonian, which has an analytical solution in this specific case. In other cases, you may have to evaluate these epsilon A's numerically, but they would still be, this A and B will still be eigenstates for H0. So this is extremely useful because it lays the foundation for a two-body state, a general two-body state. So the thing is that if I take H and act with AB, which is the same as H0, plus the interaction piece, acting on AB, this is different from an energy. So I just label this as an E. So I will use lowercase letters for single particle properties and uppercase letters for more than single particle properties. So this is not the same. So A and B is not an eigenbasis for the exact solution. However, as we will see later, since A and B are orthonormal functions, then the two-body state is also going to be an orthonormal basis. So we can make a orthonormal basis, so which I'm now going to call a phi of AB, which is now simply going to be an AB here. And I'm going to let this AB now, the two particle levels, I'm just going to let this become a single particles. No, not a single particle, but just one index. So AB is now a configuration. So I call this one for a configuration of two particles. So if you think of you going back to the image which we made in the previous lecture, I would now say that if I have two particles here, this is a configuration. If I have two particles here, that would also be a configuration. If I have 6 particles, then this could be a configuration if these 6 particle states are filled. So that makes a many-body configuration. But then, since we always want to simplify, if you look at, for instance, this specific state which we put in here, if in that specific case, we would also have the 0, 1 spinor, and in total we could make 4 states. But instead of labeling them as 1, 0, 0, 0, 0, 1, 0, 0, and so on, we would just call them state 1, state 2, state 3, state 4. So if you go back to the labeling which we had here, where we have slots, where each slot points to specific single particle quantum numbers, you could now think of making new slots where each slot points to a two-particle configuration, and so on. So when I use the word configuration, I actually mean a way to distribute the single particle states in different sets of quantum numbers. And in principle here, since these are fermions, you can do combinatorics without replacement. And that means that you have a binomial factor of possibilities. So before we now set up, let me just say one small thing here, because that tells you about how the dimensionality grows. So we have defined a configuration. That's one possible way of distributing the single particle states in a set of single particle states, okay? So let's just sum some of these things before we calculate the final thing. So when I say configuration, That is a way to distribute one or more particles. We can have a one particle configuration to distribute one or more particles in all possible single particle states, in all possible computational basis states. And in our case, the computational basis states are single particle states. So I'm going to give a number to that, and I'm going to use a label. So this all possible single particle states, I'm going to distribute that with, call that for lowercase n. So if I have fermions with n states, so these are the possible computational basis states, which in this case are single particle states, which we know how to solve, and n particles, n fermions in our case, the number of possible configurations, configs, is just a combinatorial factor which is given by a binomial factor, and that's going to be given by n, little n, and n, which again is n factorial divided by n, and we're assuming that little n is larger or equal than n minus n factorial, and multiply with n factorial. So this tells you about the complications you can have in many-body calculations. So one thing is that in principle, this little n is equal to infinity. So we have to make a truncation there. So we need a finite basis set. The number of particles, if you look at an atom like neon, or you take a nucleus like tin, you have 100 protons and neutrons. This is still a finite number. However, you can distribute this in an infinity of states. And that clearly puts a constraint on what you can do with different many-body methods. And typically what you will do is to make an approximation on n. You will never do infinity. And then sometimes the number of basis states you get here is too big. And then you make a new truncation. And then you limit the number of configurations. So these kind of two truncations are very common in many-body physics. The first one is to truncate the computational basis states, which are used to construct your states, and then to make a truncation in the total possible number of configurations. In many cases, you cannot quantify the error you make by doing such a truncation. And then what you typically do then is that you run a calculation with a given number of single particle states, or this little n, then you increase it, and if the energy doesn't change by a parameter you have chosen, then you would say that I'm happy. It looks as if it converges. In some cases, you can actually make precise error estimates on what you leave out. And again, this is a small digression. If you use a harmonic oscillator as a basis, you can actually quantify the error you make by making a truncation here. And that's neat, but you cannot do that with a general basis. But some specific single particle functions are extremely useful. Okay, so this was a small digression, but I think this is important because it tells you about the limitations of what we can do. So it's very important that if somebody tells you that my many-body method is the best possible one for that specific system, you always have to be aware of what are the limitations. And all these methods have their pros and cons, as we said yesterday. If you can diagonalize, that means that you diagonalize in a Hilbert space which is defined by this number. And when this number is larger than 10 billions, typically, there is no way you can diagonalize with present high-performance computing facilities. And then you have to search for other methods. So every method has its own pros and cons. If you do stochastic methods like Monte Carlo methods, you can target the lowest lying state with a given symmetry. If you want excited states, it's much more difficult. Okay, so what we did was to calculate this quantity here. And we found that if we use that specific basis, which now happens to be an eigenbasis of the single particle operator, then this AB is an eigenbasis, a two-body eigenbasis for the two-body H0 operator. But it's not an eigenbasis of the full problem. But still, we can compute things. And the interesting thing now is that, and this lays the foundation for one of the many-body methods, is that we can actually define now a two-body state, AB, which is a linear combination of these basis states. So when I have such a complete orthonormal basis, I can obviously make this sum here, I0, up to the dimensionality, d minus 1, and then I have some overlap coefficients, Ci, and then I have my basis states. No, I should actually have a sum here. Yeah, so these are the configuration which I have. So this C of this I is now a compact way of writing these states A and B. So I can expand in terms of this basis of determinants. So if I have two particles, I can now construct all the two particle determinants by distributing my particles in this basis set. So as an example, suppose now that this little n is 100, and I have two particles. The possible number of configurations, of configs, is then obviously equal to 100 divided by 98 and multiply with 2 here. And that gives us 49 times 50. So that gives us 49 times 25 possible configurations. So this is a doable number of configurations. So that means that in this specific case, you would have a matrix of dimensionality of 1,000, roughly times 1,000, and you can diagonalize that one easily. So you can set up all these two particle configurations and diagonalize. Then you have 100 single particle states. You see the pattern here? You can increase this quite a lot. And you would normally see that for two particles only, this is a tractable problem. If you're having 100 such levels and 20 particles, then you would not be able to diagonalize that problem anymore. So one of the methods which we will meet a little bit later, which is called full configuration interaction theory, means that you set up all the configurations in that space, and that's why it's called full configuration. And you're setting up a Hamiltonian matrix, so you're letting the configurations interact. And that's why you have the name full configuration interaction theory. So that means you setting up all the Hamiltonian matrix elements and then diagonalizing that matrix. We are coming back to this a little bit later. That's going to be the first many-body methods we encounter. And if you can diagonalize, you have actually solved the problem. Okay, so let's now go back here and try to calculate AB for HI, the interaction. So that's going to be the last part here. So let's do that. So this term is going to be equal to 1/2. And then I have dx1, dx2. And then I'm setting up the wave function ansatz in terms of these basis states. And then I have a potential which depends on x1 and x2 here. I'm just writing that in this generic way. No, not that one. Sorry. Now, not minus, getting towards the end of the lecture here now. Now, this is something which I cannot simplify. So I actually have to consider all the four terms. And the reason for that is that we have a two-body interaction. So in the previous case, we had a Hamiltonian which acted only on one particle at a time. But now, if I look at the first term, I cannot simplify that any further. So I would have just 1/2. This is the first term, dx1, dx2. And then I get a of x1. And then I get b of x2. I have my interaction, because now I cannot separate this unless the interaction is separable. So sometimes you have interaction which can be separated in an x1 part and an x2 part, but in the general case, you cannot separate the degrees of freedom. And that means that you have to evaluate the integral. So this is then multiplied with a of x1 and b of x2. And we are going to write this in a compact way. So we have 1/2, and then we have ab, v, ab. This is a notation which we will use. So when you see that compact notation, it simply means this integral. Now, all the other terms can also not be simplified. However, there are some symmetries here which allow us to simplify things. And people have actually tried to see if you experimentally can break these symmetries. So will there be a dependence on x1 and x2, whether you integrate first one or the other one? So we have a translational invariance. So if you look at the last term, if you take this term and that term, when I've said that the potential energy, V x1, x2, this is an important symmetry, is equal to x2, x1. So in general, the potentials depend only on the relative distance. If you think of the Coulomb interaction, it depends on the relative distance between two particles. If you look at the strong force, the same. If you look at the electroweak force, the same. So many forces in nature have that symmetry. And people have tried to see if this symmetry is broken. And till today, within experimental uncertainties, there are no signs that for some of these forces or interactions, the symmetry is broken. People have actually tested in very refined experiments whether the Pauli's principle is broken. And still within numerical uncertainty, they cannot see any breaking of the Pauli symmetry. So there are some symmetries which we believe are present. So if I do that, and now you have to remember that x2 and x1, if you now look at the two last terms, this term multiplied with a potential and multiplied with that one, it has a minus term, a plus term, that becomes a plus. Since these are dummy variables, I can interchange x1 and x2. And then I get the same expression as this one. So the first and the last terms, they give the same. So let's just write that one. And then I'm just going to sneak in 2 more minutes, and then we will have the answer. So I'm going to write this as a 4. So the last term. And due to the symmetries, I will have 1/2 and it's going to be BA or V, BA, but that is identical with 1/2 of AB or V and AB. And then if I look at the second plus the third term, I can do the same. And the second and the third term are going to give me 1/2. There's a minus. And they're going to be given by AB, V, BA. The second term. And then the third term is going to give us the same expression, except that it's in the bra side where you change A and B, but it gives the same answer. So we are going to get minus 1/2. And then I have AB, V, BA. So finally, what we have then is that the expectation value of this specific state we wrote of AB is actually given. So this was a compact notation where we now used this one to identify the full two-body wave function. And now it's a little bit sloppy notation, but what we get is actually AB of V times AB minus, and then I have AB, V of B of A. The last term comes only due to the Pauli principle and the anti-symmetry. And it's normally called an exchange term. So this is called the direct term, direct, and this has the name of the exchange term. So this type of integrals, when you have a two-body interaction, is something which we now can use for many particles. And with many particles, what you're going to see is that when you have only a two-body potential, you will only have to deal with two-body interactions. So if you go back to that expression, that general expression which we wrote right after the break, this integral which you see here, this integral, when you have a two-body interaction, that integral simplifies to at most a sum over two-body integrals. So instead of having, if you have 100 particles, you have a 100-dimensional integral, but you can actually rewrite this as a sum over integrals with only two particles at a time. And that's an important simplification when we are calculating expectation values. So next week or next Thursday, we are going to generalize this problem, which you see here, to more than two particles. So the way we typically count in this course is 1, 2, 3, many. So few body problems often up to 3 particles. That's also the way I learned to count, and I still count that way, 1, 2, 3, many. Yeah.
I just want to make sure that the ABs on the left side of the equality and the ABs on the right side, they're not the same ABs.
Yeah, that they're not the same. Yeah. So this was the, as you said, this is the two-body state, the full two-body state, whereas these now are just indices in an integral, and they are defined in the way we did here. So when I from now on, when I'm writing something like this or something like this, it will always be an integral. Always. Okay,
I'm not sure I quite understood what you mean, that they're different ABs.
No, the states. So if you look at the original state we started with, we actually started with this state. But I use this shorthand to indicate a many-body state. But now, when I went to the final calculation here, I ended up labeling this A and B as just the integral here without the exchange term, without the other term. So it's a little bit sloppy notation. I should actually have put something here like a tilde on top of it to indicate that this is not exactly the same. It's common to simplify calculations to bring these together. And then you talk about a fully anti-symmetrized interaction. If you're dealing with identical particles of the type of fermions. And then instead of you calculating both this term and that term, you simply just list one. Because when you run the calculations, then you have both baked in the definition of the interaction. Yeah.
One last question.
Yeah.
This sort of photon you do down there, does this sort of generalize to multiple body problems?
So as I said, when you have only a two-body interaction, your many-body integral reduces to a sum of two-body integrals only. If you have 100 particles, it will be a sum over all the ways you can combine two particles among 100, but they will only involve these type of integrals. If you have a free-body interaction, then you can have three particles, and then life becomes a little bit more complicated. Then you have more integrals. So instead of having some few hundred, you can have some thousands. So if you can avoid dealing with free body forces, you want to avoid it. And in quantum chemistry, solid state physics, atomic and molecular physics, you get easily away with two-body interactions only. Those are the most, and electromagnetic forces. That is essentially what you have. If you do nuclear physics, life is a mess. Okay. Should we take a good weekend break? And I will present the exercises. I'm going to typically send an email right over the weekend with plans for the next week. And next Friday, we will also have exercises. And then we will use this session both for theory and exercise solutions.
How long will, how much time do you expect this to use on exercises?
The hope is that you can finish them within this session. So it's only 2 or 3 exercises at most.
So next week we'll have lectures from 10 to 12?
Yeah.
Okay.
Or we can change.
For me, it's better 10 to 12 because I have a lot of lectures. So, no, I have a lecture 12. I just love recording.
Why don't you have a fighting?
Okay, we can fight with that.
Okay.
I'll record it. Okay.
I shouldn't put that on the recording.